Okay, let's see how smoothly we can do this. This is kind of new for me to do a review session like this. So I've got the review paper in front of me, and I'm not going to spend a lot of time on these slides. We've already done these. I just want to point out, for instance, branches of science. Specifically, of course, what I'm most interested in is the natural sciences. So have a sense for, we have biological sciences and, we have biological sciences and physical sciences, and then exactly kind of what the physical sciences are. You probably already kind of know some of this stuff. The next thing I have on your review sheet is the scientific method. My favorite things about the scientific method is to be able to kind of distinguish between hypothesis and theory. So again, you probably already had a sense of that and be able to kind of know that. Then we talked about, on your review sheet, I say astronomical unit. So what an astronomical unit is actually the average distance between the Earth and the Sun, which of course varies a little bit as the Sun is at perihelion, the Earth is at perihelion and aphelion. But an astronomical unit, that's what it is. Also, I have on your review sheet what is the deal when we say something is, some of us have seen the Andromeda Galaxy M31. It's 2.5 million years ago. And kind of remember what the implications are of that. The light from that we saw the other night actually left that galaxy, which is outside the Milky Way galaxy, 2.5 million years ago. So that set of stars, the galaxy has aged 2.5 million years since that light left. Does that make sense? Then I have a slide asking about a cosmic address. So of course I don't know if you can see this, let's see, yeah, we are on Earth and we are part of a solar system. Of course, our sun is just kind of a typical star. We'll be talking more about that. And our sun is part of the Milky Way galaxy, and our galaxy is part of something called the local group of galaxies. And then actually galaxy clusters like the local group are further organized into superclusters, and then the superclusters of galaxies are kind of hanging out in the universe. That's our cosmic address. On this slide, I brought it in because I want you to know our nearest star is Alpha Centauri, about 4.4 light years away. The other thing is that within our galaxy contains about 100 billion stars. Is that not amazing or what? So those are both on your review sheet. Also on your review sheet is if this was the Big Bang, okay, and if now is here about ready to start a new year, actually human beings didn't turn up until on the evening of New Year's Eve, and the evening of December 31st. I think that's kind of fun. Then on the next part, we talked about, of course, the Earth spinning on its axis of rotation every 24 hours, and it orbits or revolves about the Sun in the time it takes in a year, 365 and a quarter days. And then the other thing is that our axis of rotation is tilted. The axis that the Earth spins on is tilted 23.5 degrees. Remember, I kind of described that relative to being perpendicular to the plane of the ecliptic. Let's see, what else do we have? Yep, there we're showing the tilted axis of Earth's tilted axis of rotation as it orbits the Sun. Now remember, it orbits what direction? And this isn't on your test. It orbits what? Counterclockwise. What else do I have? Oh, plane of the ecliptic. So the plane of the ecliptic is kind of this sheet of paper that the Earth orbits the Sun in, and also remember the other planets also orbit the Sun and generally called the plane of the ecliptic. The Milky Way, when we're looking at the Milky Way, and it won't look this stark to us, but this is the Milky Way, and we're actually looking into the disk of the Milky Way galaxy. So that's kind of fun. Let's see. Oh, and then why does it appear dusty? The reason it kind of looks like dust, and the other day I think one of y'all used binoculars to look up the Milky Way. It looks dusty because actually those are little distant stars. And the reason they look so tiny or pinpoint is because they are so far away. And actually that's one of the things that Galileo discovered with his using telescope to look at the Milky Way. Parallax. So parallax was, remember, if you put your finger in front of your nose and look at and blink, close one eye and close the other eye. Okay, what you are doing is changing your position, and as you look through different eyes, something nearby, and then look at the background. And so we said, let's see, what do I have on here? Parallax. What is it? Okay, so what you're doing is you are changing your position looking at two objects, one kind of close in that case and one far away. Then if you move your finger away from your nose, the object you're looking at is getting farther and you see what? Less parallax. So that's kind of how that happens with distance. And so we're seeing the Earth orbit the sun, of course, counterclockwise, and we can look at a star here, and 6 months later we look at the same star, and actually, since this is a relatively nearby star, it does exhibit parallax. It's here in July, and it's here in January. So the closer the object, in this case a relatively nearby star, we do see parallax as we change our position. Let's see what I got. How to find Polaris from the Big Dipper asterism. Well, two things. One, asterism just generally is on your sheet. And although I don't have asterism on a slide, asterism, okay, that is a subgroup of stars of a constellation. So you guys would tell me that actually the Big Dipper is part of the constellation Ursa Major. The Little Dipper is part of the constellation Ursa Minor. That's Big Bear and Little Bear. So on your test, I'm going to ask you something how you can use the Big Dipper, and actually we use these two far bowl stars to point to the North Star, or the North Star right now is the star called Polaris. So know how to do that. Cool. Celestial sphere. Oops, I kind of got these out of order. Oh, maybe I didn't have celestial sphere. I don't think I brought in celestial sphere. Oh, so just bear with me. Celestial sphere is that, look in your notes if you want to, but it is kind of an imaginary ball. In the middle of the imaginary ball is, I'll put an E for Earth. And what the celestial sphere is, it has these stars imprinted on it. It's a model in astronomy. It's not the way things are, but it works well. So celestial sphere. Sorry about that. Your local sky, know these terms. Zenith in your local sky is right above you, and then we go out to the horizon, and this will give you direction. Okay, and then we have kind of how far above the horizon you are is called altitude. So the direction is kind of the in this case it says southeast, but it's the north, south, east, and west. Sometimes we can break that up into degrees. Meridian goes from due north through your zenith to due south. So meridian is an entire line. Let's see. So we talked about sometimes it's nice to know, for instance, how far above the horizon an object is. And what we can do is extend your hand, you extend it out, and most adults then, this span right here from your pinky to your thumb is actually 20 degrees. Your finger is 1 degree. Your fist is 10 degrees. So kind of know those. Let's see. So we talked about how stars will move counterclockwise around Polaris throughout the course of a single night. And if you were to go ahead and kind of make a look at the star here, star here, star here, you could put those images together and make these things called star trails. Now, the thing, if you are at the poles, then Polaris would be what? At your zenith, right straight above you. And if you were to kind of look at those star trails going counterclockwise, by the time you got down to the horizon, actually, you would see these stars going from left to right. Make sure I got that. Left to right. Yes. Left to right along the horizon. If you're at the poles, now this would be looking due north or south. Okay. Oops. No, darn. Due east or west. If you're looking due east or west, okay, then actually the North Pole, if you're at the equator, is going to be right on your horizon. And if you look out, then you're going to see your, this would be looking, let's see, make sure I get this right. This would be, if you're looking due west, then you're going to see them go, yeah, you're going to see them go from the up to the down, okay? So that's kind of how those star trails would look. Star trails for us kind of at the horizon make this slant like this. Let's see, what else do we have? Star trails. How can you determine your latitude from the North Star? So if you're ever lost, remember we said you can use the Big Dipper asterism to find the North Star. Use these bold stars to find the North Star. And actually that latitude, the angle that Polaris makes with the horizon, that angle right there is your, that altitude, excuse me, the altitude right there, that is your latitude on Earth. So that's kind of fun. Let's see, it's right up here. All right, so the next thing is you need to know some major lines of latitude. So of course we all know the equator, that's 0 degrees. And then there are two 23.5 degrees. Okay, we have the Tropic of Cancer and the Tropic of Capricorn, know those. And then we have 266 1/3 degrees. And this is, of course, north, south. This is the Arctic Circle, and this is the Antarctic Circle. And then hopefully you guys would tell me that this is 90 degrees north, North Pole, and this is 90 degrees south. So those lines of latitude are important in astronomy. Okay. All right. Now, when we talk about other planets coming up, we're going to see that if a planet's axis of rotation is not tilted like this, 23.5 degrees, it has no seasons. So honestly, at the crux, and there's different outcomes from the Earth's tilted axis of rotation, but just the fact that its axis of rotation is tilted is enough to give us seasons. Okay, so yeah, there's going to be a question on there about Eratosthenes. Isn't this cool what he did? He actually recognized that if you're at different locations on the Earth at a given day, you are going to, the angle from the sun is going to be different because of this curvature. So he actually then, let's see, I don't know, can't remember exactly how he did it. Probably must have been one of the equinoxes. So at the spring equinox, actually at 23.5 degrees, the sun is right overhead. Maybe he didn't do that, but he looked at a location where the sun was right overhead, and then at the same time of day, he could see that the sun made an angle of 7 degrees here, and he said that that must be 7 360ths of this distance right here is 7 360ths of the entire circumference of the Earth. So that's pretty cool. Let's see. So Ptolemy, actually, where is his name here? Maybe it's not on here. But what we're looking at here, what is this question here? Keyword is geocentric model. Okay, so the geo meaning Earth, so the geocentric model of the universe puts Earth in the center of everything. And it kind of makes sense because it looks like the sun orbits the Earth, even though it doesn't, right? Stars orbit the Earth. So that's a geocentric model, and Ptolemy is kind of the last gasp at that. Let's see. Heliocentric model, which of course is the way it really is. Helio meaning sun, centered. So heliocentric model is the way it really is. Okay, and with regard to, I mentioned Ptolemy, with regard to this would be what, a geocentric model, and this was Ptolemy's idea, and he actually, in order to explain, and this isn't on your test, this idea that the planets, this is a planet orbiting the Earth, right? Well, I can't remember. I guess I shouldn't say that. That's on your test, the retrograde motion. But so the thing about planets is planets usually move one way. Okay, planets usually move this way, but sometimes they appear to go back, and then they go back along their way. Planet, planet, back. Okay, planet, 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 backwards. Okay, this is against the background stars, and this this backward motion actually, the way Ptolemy explained it, was this idea to introduce what's called epicycles, where basically the planet would be orbiting the Earth, right? It's kind of weird, but it actually had these little epicycles that it would orbit, and that kind of accounted for the backward motion. So that's that. Let's see. Okay, now on to, well, I'm not sure why I have this in here, but Copernicus isn't necessarily on your test, but remember Copernicus actually had the sun-centered model going on. So that's the heliocentric model. Tycho, oops, oh darn it. I got in the wrong picture. Ugh. Go out and look at a picture, not of Copernicus, but of Tycho Brahe. You're just going to have to do this if you want to. The thing about Tycho Brahe is he had all of these, I call them toys, but he had cool instruments. And the thing about Tycho Brahe was that he used those instruments to make measurements of motion of objects like planets and stuff. So he used instruments to look at motions, okay, of planets and other things. Now, the thing about Tycho Brahe was he could not go ahead and, after looking at those motions, anticipate where the planets would be using the heliocentric model, using the sun-centered model like he was trying to do. So that's Tycho Brahe. Sorry about that. So then actually Tycho Brahe, he hired Kepler. I'm looking at my notes here. Tycho Brahe hired Kepler, and Kepler came up with 3 laws of planetary motion. And on my review sheet, I say you're going to need to know the 3 laws of planetary motion. So Kepler's first law described the shape of the orbits of the planets. Kepler's second law talked about basically, this is law of equal areas, so you could state it that way if you wanted to. The other thing is, hopefully you would call this what? Perihelion? Perihelion, close where the planet's closest to the sun, and hopefully you would call this aphelion. The planet is farthest from the sun. Oh, go back. So, and I kind of go on. So the thing about his second law is that a planet moves fastest here. Oops, fastest. And slowest here. That's it. And in doing so, it sweeps out, these would be equal areas. Those are 2 equal areas. Okay, his third law actually is the one that feels so dry. P squared, which means the orbital period, orbital P, is equal to A cubed, where that is the its semi-major axis. So think of that as the distance from the sun. Kind of. Okay, so basically it said that the farther away the distance is, farther from the sun, then it actually moves more slowly because P increases. Okay, and that is, sometimes students will say, is that a gravity thing? And yes, that's a gravity thing. So that's his third law. Very good. Okay, on to setting up for Newton's laws of general motion. You need to know or have a sense for, what do I have here? I'm on the second page. Yay! You need to have a sense of what speed is. Speed is distance per time. Velocity then adds speed and direction. And acceleration is a change in either speed or direction. So acceleration is a change in velocity. So all 3 of these are examples of changing in velocity. If we are at what? Speeding up. If we're keeping the same speed but changing direction, like we said, orbiting objects have acceleration because they are changing their direction of motion, and this one's coming to a stop. Those are all examples of acceleration. Newton's general laws of motion, 3 general laws of motion. So this first one is that an object will continue to move in the same direction with the same velocity unless acted upon by an outside force. This one, Newton's second law of motion, says that the acceleration an object will experience is equal to the force that's applied. So acceleration times the mass will be, here's the relationship between the acceleration object feels and the force applied. F is equal to m times a, where m is the mass of the object. His third law is that for every action there is an opposite and equal reaction. So just know that. All right. The thing on this slide is I know a lot of you answered this homework question this semester. What is momentum? And momentum of an object, now it needs to be moving. If it has zero velocity, it has zero momentum, but you take the velocity of the object, how fast it's moving, the direction it's moving, times its mass. That will give you its momentum. This one, generally know the 3 subatomic particles, okay, that make up an atom. And kind of where they're located. A lot of times students come into this class with this knowledge already. Also know I've got something called the atomic number on your review sheet. Atomic number is the number of protons in the nucleus of a particular atom. Now the thing that's important about protons or atomic number is that gives the element its identity. So generally know those things. Generally know that all matter is in motion. So one of the things, hopefully you can see that these arrows are only this long, these arrows are this long. This is actually a higher temperature. So these has more motion, more kinetic energy. So kind of know that. So more motion, higher temperature. Okay. Now we talked about 3 temperature scales. And this is the one where you get your weather. We say how warm is it outside? That'd be in degrees Fahrenheit. These 2 are metric. Okay. Now, Kelvin actually is the coolest, no pun intended. It's the most impressive temperature scale because it actually, at 0 Kelvin units, it actually means something. So on your test, it's probably going to be a question probably about the Kelvin temperature scale. 0 Kelvin is something called absolute zero, where all molecular motion stops. Because you guys told me that as you cool something down, it moves slower and slower. Okay, it has less kinetic energy. Well, at 0 Kelvin, matter has no motion. So that's how that works. Let's see, temperature scales. I'm kind of getting down there. What else do we have? Okay, so if you toss a ball upward, of course, the gravity of the Earth is going to make it slow and slow and slow, and up here it's going to stop. So up at the top of its swing, it totally stops. Up here, it has basically, 0 kinetic energy because it's not moving, and it has the most potential energy. And then here, right before it splats, I think you guys told me in class, it has the most kinetic energy, most KE, and it has basically 0 potential energy because it's like, so. All right, moving on to the moon. So a few things about the moon I want you to know for your test. One are these terms called perigee, and is it on this one? Yes, here it is. Perigee is when it's like perihelion. Perigee, though, is when the moon is closest to the Earth, and apogee is when it's furthest from the Earth. Let's see, I've also got on there, generally know what a supermoon is. So a supermoon is when the moon is in its full phase and it coincides with also being closest to the Earth at perigee. Let's see. Yep. So you're generally gonna, here's one. I just brought this in because I'm actually not asking you about the phases of the moon, which is really kind of weird for this test, but I think it'll be fine. I do want you to know that terminator, when you look up at the moon, that is the break between the illuminated part. Remember, it's illuminated because the sun's shining on it versus the dark part. So that's the terminator. It'd be back, right? I also want you to generally know, near side and far side of the moon. So this is not how it is, this is how it is. Remember that the moon spins on its axis of rotation. We call that synchronous rotation, which is not on your moon, which is on the test, which is kind of weird. But we have, I'll put an N for near side and an F for far side of the moon. Okay, synchronous rotation, sorry, I forgot to finish that thought. You guys know that the Earth, not the Earth, you can see the moon rotating on its axis of rotation here. The amount of time it takes to do that is about the same or exactly the same as the amount of time it takes to complete one orbit, which is 29.5 days, I think we said. Okay, so the moon actually is why we have oceanic tides on the Earth. So what happens is the moon exhibits some gravity, and a pole of gravity actually kind of lifts up the large bodies of water, and the Earth spins underneath it. Now it lifts it up on the near side to the moon and also lifts it up on the far side to the moon. Wait, that's, you know what I mean. So let's see. I also have here spring and neap tides. Oops. So remember, the deal is that we'll have spring tides. Darn it. Spring tides happen when the sun is working in conjunction with the moon. And that happens at new moon and full moon. Okay. And neap tides are a diminished tides. We'll still have tides, but they won't be very high, and that happens at the quarter moons. And the reason of that is because the location of the sun is kind of making a drag on the gravitational pull of the moon. So I want you to generally know the eclipses. Know that a lunar eclipse will happen in full moon, a solar eclipse will happen in new moon. Okay, and the reason they don't happen every month is because this blue sheet right here is showing you the path of the moon as it orbits the Earth. That path, that plane of the moon orbiting the Earth does not lie in the plane of the ecliptic. So that's why they don't happen all the time. There's a question on there: when is the next major solar eclipse in the United States? And it is in April 2024. Then talking about the formation of the moon, and notice in my slides, I must have gotten this from your textbook, that it's not a theory, it is a hypothesis, which is before a theory. And the predominant theory out there, hypothesis out there, is that there was an impactor. This is the impactor that slammed into the Earth while the Earth was still what I call ooey gooey, and some of the Earth kind of splashed out. That matter that splashed out kind of coalesced and formed what now we know and love to be the moon. Now, things that support that actually is that when we visited the moon, the material on the moon is very similar to the material on the surface of the Earth. The other thing is that this impact could have the same impact actually could have been why our Earth's axis of rotation is tilted 23.5 degrees. So that all is how that works. So another thing that you're going to need to be able to do on the test is to generally say what the moon kind of looks like on what this near side is. So these areas we call what? Mare. Okay, they're kind of the darker regions. The lighter regions here are called highlands. Okay, the other thing we talked about is the fact that if you were to, and we can do this with the telescope, right? If we looked close up to this moon's surface, we would see that cratered regions have some features to them called, there's a central peak there, we have some terracing here. Ejecta blanket, a very good example is that the relatively new crater Tycho has this kind of cool looking ejecta blanket. So be able to kind of describe what the surface of the moon would look like. From the moon, we brought back some rocks, and they fall into these categories. We have Mare basalt, Northositic. Now, the basalt looks like kind of the Hawaiian Islands, lava rock. Northosite are these old sort of rocks from the highlands. And then we have these impact breccias, which were formed from the heat from the impacts that the poor little moon's been through. Then we go on to our last section. How do we see asteroids? This is a picture of an asteroid up here, kind of like a star trail, but it's an asteroid trail. Remember, you only see asteroids because the sun is shining on them and you see them move against the background stars like that. Let's see, what else do I have? We're going to talk about different places that asteroids are. Actually, the most common place people think of as asteroid being in the asteroid belt between Mars and Jupiter. There are two very large asteroids. There's a large asteroid Sirius and Vesta. So asteroid belt is right here. Okay, of course, between Mars and Jupiter. Remember, the asteroids are not that close together. The other location for asteroids are here. So if this is Jupiter, we kind of have a pile in front and a pile behind at these, what we call these Lagrange places. And so they actually then, these go in front of Jupiter and these go behind Jupiter. They kind of escort. They're the escorting asteroids, the Trojan asteroids. Then we have Apollo asteroids. They are our wild childs. Apollo asteroids are the ones that actually would cross, they orbit the sun, but Apollo asteroids cross Earth's orbit. Let's see, what else do we have? Then I wanted you to be able to distinguish between these three M's, and I've kind of written them in order that they occur. Meteoroids are kind of like asteroids there in outer space. A meteor is brief, okay? It's that streak. Oh yes, they call it the streak. It's the streak that comes through this nighttime sky. And the reason it lights up is that little space rock is falling through the Earth's atmosphere and burning up or being ionized. And then a meteorite, if it's substantial enough and it survives the Earth's atmosphere, that's a space rock that has landed on the Earth. All right, then on to comets. So the general location of the comets would be here in the what we call the Kuiper belt, which is kind of lies in the plane of the ecliptic, is the way I think of it. And the Oort cloud is extensively farther from the Kuiper belt. The Oort cloud is about, what does the slide say? You're looking at about 50,000 AUs, kind of a sphere around centered on the sun. You're going to want to generally know the anatomy of comet. The center rocky thing is the nucleus. Now, if it gets close enough to the sun, it will begin what I call fizzing. And so it will form this kind of coma region. It's that glowy region around, kind of around the nucleus. And then it can create these two tails. A plasma tail is straight away from the sun, and the dust tail would be kind of the arching tail. So, meteor showers. So on a given night, if your skies are nice and dark, you should see about a streak or meteor every 10 minutes. But now meteor showers is where actually the Earth is pushing through usually comet debris as it orbits the sun. This is like little chunky stuff in its way. So that is a meteor shower. And meteor showers are named by the constellation they pass through. So these you might recognize, well, you probably don't recognize quaternids, but the constellation Lyra is where the Lyrids are going to look like they're coming from. Perseus, that give us the Perseids. Orion gives us the Orionids. Taurus gives the Taurids. The constellation Leo gives the Leonids. Gemini constellation gives us Geminids. Okay, and Ursids are actually, I think, Ursa Major. So that's that. That's how they're named. And then the last thing is, this is Clyde Tombaugh. And he is the person who actually discovered Pluto. And Clyde Tombaugh's ashes have been placed in, that's my next thing. His ashes, oh, by the way, how did he discover Pluto? He discovered Pluto the same way we see asteroids moving. Basically, a little speck moving against the background stars. You're like, are you serious? I'm like, I'm serious. That's amazing. So that's how he discovered it. And so this actually is a picture. Isn't that awesome? This is a picture of Pluto taken by the spacecraft New Horizons as it flew past. And actually New Horizons is headed outward, out into the Kuiper belt, still sending back, or I think still potentially sending back data. My point, what I started to say, is upon New Horizons, the ashes of Clyde Tombaugh, the spacecraft has his ashes. So we may have demoted his planet, but his ashes passed, literally passed the now dwarf planet Pluto. So I hope this was helpful.